Okay. Well, thank you very much for giving the opportunity to be here. First of all, I would like to thank the faculty for giving the opportunity to be here today, and all the staff members as well, and all the professors that I already know since many years already, that I've been in contact with them all the time, basically since 2018, 2017. And for me, actually, it's a pleasure to be back to the TVUT, and for me, it makes me very happy to defend this habilitation here right now. Okay, so my defense will be structured with the following topics. I will try to be very brief about the mathematics point of view, what I'm doing in the last few years, actually in the past since 2016, that when I started for real to be a mathematician. And then I will talk about a little bit about my research, not like maybe 5 minutes, maybe a little bit less than this. And then I will finish with a summary of my teaching and my research, what I'm doing in the past few years. Okay, so let's start with the Banach space theory. For me, this is going to be very personal, so I will give my vision of what Banach space theory is. For me, it's a central part of function analysis, which at least most of the universities that I've been to consider function analysis as a mandatory topic. So it's mandatory for the students. So for me, a Banach space is a space where you can measure the length of the vectors. So you have a bunch of vectors in this space, and you actually have the skill of measure how big these vectors are. Also, that you can calculate the distance between 2 points. You give me two points in this space, and I will be able to calculate the distance between these 2 points. And also, the most essential part is that you can operate the way you want, and you never go out from this space. So this is the kind of space I'm considering here. Well, why to study Banach spaces? Because it's the right, I don't know if it's the right, but it's one of the approaches for generalizing Euclidean spaces. For instance, we are living in the three-dimensional world, so there are several, I would say several just to be nice, but most of the phenomena in the nature have a kind of infinite dimensional approach, because it's much easier to see what's going on here and then looking down than on the other way around. So this generalizes Euclidean spaces in the sense of two-dimensional and three-dimensional spaces. So it kind of gives the global vision of this kind of spaces. So the problem is now when you start working with infinite dimensional spaces, the intuition goes away. I mean, sometimes your intuition goes to the right direction and you can prove something, sometimes it doesn't. So sometimes it's very tricky to work with this kind of spaces. But also, at the same time, you can use the finite dimensional approach that we know what's going on there and try to extend it to infinite dimensional spaces. That's what actually a lot of people do as well. For me, by working with infinite dimensional, like I said before, it gives you different ways of getting different approaches for different problems. For me, I always say to my students that to study infinite dimensional Banach space is like to fly in the sky, and then you see everything what's going on in Earth, because you can see what's going on from a good perspective in this sense, right? And of course, the other part is that it provides several tools for different areas of mathematics, like I'm going to talk about a little bit in a while. But formally, what a Banach space is. So a Banach space is a vector space. Again, just think about the space where I can touch the points somehow, and I can define a norm, which means my distance. So you can give me my points, you can give me the point, and I can calculate the distance between these 2 points, and I can operate with these distances all the time. Okay, and the last thing is that every Cauchy sequence is convergent and plus converges to a member of the space itself. This is the thing that I was telling you about, that you can operate the way you want and you never go out from the space itself. Okay, so this is the definition that you do in the first class of functional analysis course when you want to talk about Banach spaces afterwards. So actually this is the simplest way for students, because they will know what a vector space is, they will know what real numbers are, complex numbers are. They will know what a norm is, so they understand this language when they are in the last year of the undergraduate, right? Okay, so but why to study infinite dimensional spaces? I said before, but I just want to emphasize a little bit more that functions in general, they don't live in a finite dimension structure. To face them, you have to go to infinite dimensional spaces. I won't enter in any detail, but this is the way it is. This is a fact. Actually, we show also in one of the first classes of functional analysis that functions cannot be faced by a finite structure, right? So, for instance, I'm giving you here 3 examples. The state of a particle is a vector in an infinite dimensional Hilbert space, for the ones who know what a Hilbert space are. The velocity field at a point in the space is a function, which means that you go back here again, and then you are in the functions sense. So you have to work with infinite dimensional space. A sound wave, for instance, of course, is a function. And you have to treat it also as an infinite dimensional space. And of course, I put it here just to laugh it up a little bit. That nerding out a bit is also part of the game. And I'm saying this as a joke, but it actually is not. Actually, most of the things that come up, at least in my research, comes out of curiosity, not because we are looking for some applications, but just to know what's going on. So what happens if I go to infinite dimensional Banach space? What happens there? But just for out of curiosity, and then afterwards you find out something more interesting in this sense, right? So actually, I'm joking a bit here, but actually this is not really a joke. This is actually what we do in most of the cases. Okay. So I just put some examples here of. I don't want to pay attention in the whole mathematical stuff, but I just want to know, for instance, the space of sequences. You take a sequence, so a list of numbers, which happens all the time in the real life. For instance, you put your name in the platform in some computer. You have your age, you have your name, you have your surname, you have your credit card number. So you have a long list of things happening at the same time. So you can face it. This sequence has something like this, and then you treat it as a Banach space. So you can work with this infinite dimensional space, and you can work with it by calculating, by defining the distance you want to work there, and so on. Okay, why these spaces are so important? Because it appears in different areas of studies. For instance, in signal procedure, for instance, some ability theory, in Fourier analysis, and etc. The same thing happens with the big LP, which are actually functions. This time you do the same story, and also you have some applicability in real life. Well, in real life, probability, if you think that this is real life enough, I think this is reasonable, at least. Okay, maybe you cannot believe that I'm a Banach space theoristic. Maybe I'm not a real guy, but at least probability, I think everybody agrees that this is real life for sure, right? So quantum mechanics and the partial differential equation, etc. Can do the same thing with the spaces of continuous functions, which has applicability in numerical analysis, for instance. And the more recent, the study of the Lipschitz free spaces, because they have applicability in optimal transport and mass transportation, computer sciences, etc. Okay, and I just want to finish with the C-star algebras, because I know there's some expertise here in the audience, but they also are not entirely only mathematical, because they have some applicability in other areas too. Okay, so I just listed a bit here these applications. Of course, the list is much longer, if you will, but I just put some examples here just to use, so that you know that all these areas here use Banach space theory as a tool to tackle their problems. Okay, and like it can be a language, it can be to tackle a problem itself. Actually, I was talking to the dean right now that we can actually provide some tools for the engineerings, for instance, to work with these tools so that they can tackle their own problems, right? Okay, so there's a diagram in a book that I really like, The History About Banach Spaces, that the author puts this kind of ball here, and then shows Banach space in the center of the whole thing. And then you can see here next to it all the areas that use Banach space theory has a language, at least has a language. Okay, and the rest, then you can use the results about Banach spaces and etc. But at least has a language, they use all this stuff. Actually, I'm in contact with some people from South Korea that they're using our languages in quantum informations, for instance. And quantum information is nowadays very, very on fashion, I would say, in many ways. Okay. Okay, I will briefly talk about my research now. I don't want you to pay attention to the mathematical background here. I would just comment some things. The name of my sub-area, let's say, so if you have function analysis, you go down to Banach spaces, Banach space theory, and you go down a bit, I'm in the geometry of Banach spaces. Actually, that's the area that I consider myself in. So I'm studying nowadays Normatanian theory. Smoothness in Banach spaces, that's the topic that I start working when I came to the Czech Republic, actually, with Petr Hayek from this faculty. And nowadays, I'm working more about these three topics: lineability, Lipschitz free spaces, and the Dogaved property. This is just recent, maybe during the past 3-4 years, that I start working in these directions. Okay. Well, I mean, I just put here some papers that I think I can say that I'm a little bit proud of. This one is the first one that I would like to mention, that here we actually try to push further the theory so that we can get new result in the Normatanian direction. The same thing we did in these two papers here. Actually, these three papers are part of my thesis of the habilitation. And this problem that I start tackling here when I came to the Czech Republic, that we published these three papers here together with Petr Hayek and Tommaso Russo, were actually, both of them were was member of the faculty at that time, and we managed to publish this three paper. Actually, I'm very proud of this paper here in particular because it gives you the general picture of this problem that I didn't mention before. But you have this problem, and actually we could manage to prove a general picture of this problem in that paper. And then to finish, just two more examples that we consider lineability. That's some kind of the problem is you have some set, and I'm interested to put the whole infinite dimensional inside of this set. In other words, how can I decide if a set of things, of objects, is too big or not? Okay, so this is the kind of problems that we're tackling in these two papers. Actually, I think it's worth it to mention that Rubén Medina and Andrés Quiles, at that time of this paper, they were members also from the faculty because they're students of Petr Hayek at that time. Okay. Okay, so now I will show you my collaborators. Well, I mean, this was not easy to do it. So actually, I didn't do it. It was somebody else who did it. So all the credits goes for her, not for me. I just gave her the list of my collaborators, and that's all. And then she did that. So the thing that I want to put here was to emphasize my bosses in some way. These are my PhD advisors, Domingo Garcia, Manuel Maestre, and Miguel Martin. These two are from Valencia University. This one is from Granada University. And then I went to Korea to do a postdoc for 1 year. And these two were my fathers there, Han-Ju Lee and Yoon Song Che. And then finally I came to the Czech Republic to work with Petr Hayek, which also I consider himself one of my mentors as well. And then the rest are all kind of connected so that you can see how our world works, more or less. So you start working with one, you start knowing someone from a conference, you start discussing mathematics with this person, and then so on, and it goes. And then this doesn't mean anything. This just means that I'm getting old, and that's all. That my collaborators are increasing. This only means that I'm old enough to draw this diagram, right? And one thing that I want to emphasize here is that I love going for research stays. So that's the consequence of all these different countries here. So every time that I have the opportunity, and of course I have the money enough to be supported, or if I have my own project, I like going to different countries to collaborate with all of them. Okay, so this goes to my last part of the presentation. I think I don't know, my time is okay to finish with this very, very briefly. But I would like to comment about my teaching and my scientific activities that I've been doing in the past few years. At the moment of the application, I didn't have any PhD student, but I have an update here that I might have one in Granada University. So this is very recent. Of course, this was not 1 year ago when I applied for the habilitation, but now I do have one. Master students, when I applied for the habilitation, I had 1 master student and 2 bachelor students. Now I have 3 more at Valencia University. And the Studenta Anqueta, also at that time, I put just these 2 here from Valencia University and from Universitat Jaume I, that they are all favorable. Of course, the numbers here are completely different from the CVUT. Each university, they have their own system, of course. And now I'm at the Granada University. I'm not in Valencia University anymore. I'm a professor there. And also, from this semester, I got also a favorable Anqueta, right? So if you ask me to select some 3 publications, I would select the ones that I mentioned before. Like, for instance, this one, the first one that I said, the one that I told you that I was proud of, and the one with Ruben Medina and Andres Quiles that I mentioned before as well. Nowadays, I'm author of 37 publications. But of course, like I said before, this means that I'm old enough because I started publishing in 2016. So my H-index is 7. Times of cited without self-citations is 85. I have been in all these universities, has research stays, and one thing to finish my presentation is that I was an IP for PI of a research project recently that it finished very recent. And I think that's all. Thank you very much.
Thank you very much for your lecture where you introduce us what Banach space theory is and short overview of your research and teaching activities. Now I open the session for questions, and I would like to ask audience to put questions. Professor Železný.
I'd like to hear a little bit about the impact of your achievements. So did other people follow up on some of your results?
Yeah, sure. I mean, I mentioned here very briefly that my H-index, it's 7. This means that I have at 7.
It can be citations like shallow citations and actually, grasping the nature of your achievements and doing something more. So that's what I'm asking.
Yeah, well, I mean, I would say so because I have my first paper, for instance, that I published when I do the PhD, a lot of people have cited because they either were using the techniques that I was using at that paper and also creating new ways of seeing different things.
So that was, for example, what results, if you could say that in plain language?
Sorry?
Can you describe kind of intuitively what you have worked out so that other people followed up?
Okay. So in this paper that I mentioned before, we were kind of studying some differentiability for these distances that I was talking about before. So how smooth are these distances in the sense that how can I construct the unit ball in the perfect way? Because when you go to infinite dimensional spaces, you can actually the ball of the space can be like, I mean, the ball in the real life is a sphere, right? It's a ball. Just you can draw like this. But in infinite dimensional space, the ball can be squared. The ball can be triangle. So I'm not interested within these points anymore because I want to smooth it up at the best possible way. So this means that I want to be the ball like this. So intuitively, maybe we're doing something like this to try to construct a ball or to help to construct a ball which would be smooth like this, and I could go from one place to the other in the smoothest way, as smooth as possible.
The interest of the community, right?
In my surrounding, yes. Okay. In my surrounding, yes. Mm-hmm.
Thank you. And other questions come from Professor Havlena.
My background is control engineering. In control engineering, the core representation of the dynamic system is an impulse response. And these animals live in Hilbert space. Could you briefly explain what is the core difference between the Banach space and the Hilbert space?
So Hilbert space is just a particular case of a Banach space. So if you understand what's going on for a Banach space in general, in particular, you'll be understanding what is going on in the Hilbert spaces. Of course, Hilbert space have a very nice structure because it's very similar to finite dimensional spaces. So it can work much nicely in Hilbert spaces, but if you understand, that's what I was saying at the beginning, if you understand what's going on from this point of view, you understand what's a Hilbert space is better from this point of view.
Professor Clear.
So my question is related also to the impact. So your citations came mostly from the field of mathematics?
Yes.
Or is there any citation, for example, from quantum informatics or something like that?
No, not yet. Actually, I met this group in South Korea who are doing quantum information theory, that they are using Banach space theory not long ago. And one of my well, maybe this is too ambitious, but maybe one of my goals for the future is to try to collaborate with them at least telling them what I know, and then they tell them what they know so that we can combine things together. But no, all the citations came from the mathematics point of view, yeah.
Thank you. Professor Kittler.
Optimal transport is often used for normalization in machine learning.
Yes.
Are there any results, recent results that would impact on the use of this tool?
I know they have, but I haven't collaborated with in this sense yet, because Lipschitz free spaces, that's the part that you're saying now, I started working not long ago, maybe 3 years ago or something, but I know people who are collaborating with people from computer sciences or data analysis or something like this, that it's close related to this transportation cost and optimal transportation cost and things like this. Yes, they are, but not from me.
Thank you.
Thank you. Are there any other questions? Seems not. Then I close the session devoted to your lecture. Now we will have a short break. The meeting of the council will continue in 5 minutes in the room number 80. I explicitly invite you as a candidate, members of our committee, to join. We will continue with the public part of the habilitation procedure.
Okay, thank you.
Okay, thank you.
Thank you very much.